What is a nuclear reaction? What does reaction cross-section mean? In this lecture, we will describe the main features of nuclear reactions, and you will learn how to measure the so-called reaction cross-section. Nuclear reactions are processes triggered by the interaction between an incident particle, the projectile, and the nucleus, the target. The result may be the modification of the nuclear structure and the production of particles of different nature with respect to the projectile and the target. The incident particle could be, for example, a nucleon, a line nucleus, or a photon. In general, a two-body nuclear reaction is represented in the following way. A is the projectile and X the target nucleus, while Y and B are the reaction products. A and X are called input channel, while B and Y are called output channel of the reaction. Nuclear reactions present an extremely varied phenomenology, but they can be identified by some general groups. When B is equal to A and therefore Y is equal to X, the reaction is defined as diffusion or scattering. Moreover, if Y and B are produced in their ground state, the scattering is called elastic, while it is defined inelastic if the products are generated in an excited state. Moreover, a nuclear reaction is called radiative capture when the nucleus X captures the particle A and then emits a gamma ray. When the product Y is different from X, the reaction is also called transmutation, since a change of chemical elements occurs. It is important to point out that, in general, several products can be generated by the same projectile-target pair. For example, the collision of a neutron with the nucleus of aluminum-27 can lead to the production of a proton or an alpha particle. Each of these reaction channels has its own probability of occurrence, according to the general laws of quantum mechanics. But how much energy is needed for triggering a nuclear reaction? For answering to this question, you can start from the energy conservation law. The Q value is the physical quantity associated to the variation of the rest energies of the particles involved, and it corresponds to the energy available in the reaction. If Q is greater than 0, the process can occur spontaneously. Otherwise, the reaction takes place only if the amount of missing energy is introduced from outside, for example, by exploiting the kinetic energy of the projectile. One of the most interesting quantity that you can obtain from the energy analysis of the process is the minimum kinetic energy that the projectile must have for triggering the reaction. This energy is called threshold energy. For Q greater than 0, the reaction can occur at very low energies. But how much low? Well, if the projectile is a neutral particle, such as a neutron, the reaction can be triggered even at energies corresponding to the motion of thermal agitation. If the projectile is a charged particle, such as a proton, an alpha particle, or a heavier ion, it must overcome the Coulomb repulsion barrier generated by the nucleus. But how many nuclear reactions can take place? In general, we have to say that a nuclear reaction does not happen whenever a projectile impinges on a target. This is due to several reasons. The most intuitive one is geometry. The projectile must intercept the region where the nucleus manifests its presence. In this region can be well localized or distributed, depending on the range of action of the fundamental forces that rule the interaction. For example, the strong nuclear force has a range of action of the order of the femtometer, so the interaction region will have an extension very close to the physical radius of the nucleus. In addition, the possibility of having a reaction depends on the interaction time, the so-called collision time. As you can imagine, the collision time is related to the speed of the projectile, in other words, to its kinetic energy. These and other aspects related to the quantum nature of the interaction imply an intrinsically random character of the process. Therefore, you need to adopt a probabilistic approach to correctly describe this phenomenon. For these reasons, a very important physical quantity is introduced in modern physics, the so-called reaction cross-section. The reaction cross-section is related to the probability of interaction between the projectile and the target. The definition of the cross-section has a strong experimental connotation. For example, let us consider this reaction. An alpha particle impinges on a nitrogen-14 nucleus and produces a proton and an oxygen-17 nucleus. To measure the cross-section, we can perform a typical nuclear physics experiment based on a projectile, a target, and a detector. An alpha particle beam with known kinetic energy and current is delivered to a nitrogen-14 target. The incoming beam is characterized by a section A. In this area, there will be n target nuclei of nitrogen-14. Beyond the target, the particle detector measures the proton current generated by the reaction. The reaction cross-section, sigma, corresponds to the effective area offered by each target nucleus to the incident particle. Therefore, n nuclei interested by the incident beam of alpha particles offer a total effective area equal to n sigma. This quantity, when compared to the total area A covered by the beam, identifies a fraction between 0 and 1, having the physical meaning of an interaction probability. In other words, this interaction probability corresponds to the ratio between currents of the protons produced by the reaction and of alpha particles delivered to the target. Those currents are measured during the experiment. Therefore, from the ratio of n over A, you can derive the reaction cross-section. By definition, the reaction cross-section has the dimensions of an area. In nuclear physics, it is usually measured in barn, where 1 barn corresponds to 10 to the minus 24th square centimeters. In this lecture, we have described how particles and nuclei can interact through nuclear reactions. We've seen the energetics related to a nuclear reaction and the definition of the Q value. Finally, we have learned that the description of a nuclear process requires a probabilistic approach, in which one of the most important quantity is the reaction cross-section.